PhD actually from Hopkins, from the concept department, working on Bayesian stuff with phonology. Right? And then he moved to Georgetown as a visiting professor, teaching NLP there. And now he's back here as a postdoc with David Yarowsky.
Yep.
Yeah, please.
Yep, thanks. So I'm going to talk about morphological modeling for multilingual HLT applications. So while morphology has sort of been on the back burner for NLP for a long time, recently explicit modeling of morphology has led to pretty good improvements in various HLT applications like machine translation, speech recognition, parsing, word embeddings, and a bunch of other things. So I'm going to talk about a number of projects related to improving morphological modeling, especially for low-resource languages and those with sort of rare and interesting morphology types. And these are the projects that I've mainly been focusing on while here at JHU. So I'm going to talk about a universal annotation schema for inflectional morphology, extracting lots of paradigm tables from Wiktionary, using recurrent nets for morphological analysis and generation, and finally a little bit about incorporating morphological analysis into NLP pipelines. A lot of this work fits under the umbrella of what we're calling the UniMorph project, which is led by David Yarowsky here at CLSP, and a lot of it was developed in close collaboration with John Sylak-Glassman. So both John and I have linguistics backgrounds. As Kevin mentioned, I got my PhD from CogSci here with Colin doing phonology phonetics. So there's going to be a little linguistics aside in the middle of this talk, which will be pretty obvious. So before I get started, as Kevin mentioned, John and I have been here for a while, so I think this is the start of our third year as postdocs. However, I have talked to quite a few people at CLSP who claim they don't see us around the building or don't know where we are. So this is where we are. This is a room that most of you have probably seen. This is what you see when you walk into the room that has Ruth's office. So John and I have the office right behind her desk. So if you want to stop by and talk to us, that's where you can find us in CLSP. Okay. So a lot of the foundation for what I've been working on here at JHU started with this UniMorph schema, which was a annotation scheme intended to sort of a universal annotation scheme specifically for inflectional morphology. We're focusing on inflectional morphology right now, even though we have some ideas on how to extend it into derivational. And it's supposed to be in the spirit of something like universal dependencies, but with more focus on inflectional morphology. So right now, it includes around 270 feature labels, like past, PST for past tense. They're often similar to the Leipzig interlinear glossing standards whenever possible. And these are distributed across 25 or so dimensions of morphosemantic meaning. And the way we constructed this schema was instead of trying to fit our labels to particular data sets, we started with linguistic typology literature. So actually, John did a lot of work. He took out a lot of real physical books from the real physical library, which is pretty rare. And we tried to get as fine-grained distinctions as we could, specifically so that we could cover diversity, especially in a lot of low resource languages. So as an example of how fine-grained things can get, so in our number specification, we have tags for singular number, dual number, so that's 2, trial number, 3, paucal, which means something like a few, greater paucal, which means something like a few more than that, and then plural. These are all distinctions made by a single language called Sursurunga, which is an Austronesian language. We also have a tag for inverse number, which is a morpheme type used by Kiowa, which is an Athabascan Apache language. And basically what that means is that words in that language have a default number, like the default word for stick could be plural. And if you attach this inverse morpheme, you get the opposite. So stick plus inverse morpheme is just singular stick. Because we are trying to be comprehensive, we included a lot of unique dimensions that other annotation schemes don't always include. These include evidentiality, which is a marker for the speaker's information source, and whether it's hearsay, direct sensory perception, and so on. We included switch reference, which some languages use to indicate if an NP or pronoun in one clause refers to the same entity in a previous clause. Yeah. Sure. This one? Yeah. Mm-hmm. Yeah, I think it would imply, yeah. Yeah, and unfortunately, at the moment, we haven't worked out exactly what those entailments would be. So I think you would need to do something like that if you wanted to transfer, if you wanted to, for example, in an MT setting, translate something like dual or trial to a language that only had plural. You would need to figure out what that many-to-one mapping would be like.
So I've actually worked on this problem and have a paper going into this part of the and John Sylak and I worked on automatically inducing these kind of methods from the line workflow. So that's one approach that we're taking to it. So you use in-driven approach like that, where you can use a theory-driven approach where you use other forms of logic, like figurative and trials or subject. So I can talk more about that.
Yeah, I don't want to figure out, but just I'm asking at this point because you know the Uni where it's applied to the syntax and there is a fixed set of stuff where you don't really end up with that much specialization. Set of this examples you're allowing for more.
Yeah, I think that's inevitable. We tried to include whatever fine-grained distinctions were treated as atomic distinctions in some language. Yeah, I guess we can reinterpret.
Once you've done this, you might be able to decompose each of these labels into a feature bundle that's shared.
Yes.
So dual might be, so plural is greater than one in English.
Yeah.
And a language which has dual, that would be greater than one conjoined with less than two.
Yeah. Yeah, we actually, I think some of the features were in fact designed to be conjoined in this way. And there's actually a paper that talks about some of these details, which is actually on our website, unimorph.org, currently, that has a lot of the details for some of the design choices that went into it. Okay, so I don't need to go into, I think I mentioned switch reference. There's other cool dimensions like deixis, which is something like you're familiar with, which indicates distinctions between demonstrative pronouns, like Spanish, which has aquí, allí, allá, which means here, there, and over there, and deixis. In other languages includes even more detailed stuff, like over there invisible versus over there and not visible. And I think maybe you'll end up in a similar kind of subsetting situation for this as well.
What do you mean by calling them unique dimensions?
Oh, unlikely to appear, basically not rare and not covered in a lot of other schemas. Okay. So again, this is sort of an aspirational thing, but as much as we could, we tried to ground the features in sort of universal semantic primitives. Again, very aspirational. And we tried to do this so that as much as possible, if you had one feature tag that appeared in one language and that appeared in another language, it had a similar kind of semantic meaning. So for example, the way we define aspect and tense is in relation to the more primitive semantic elements like situation time, utterance time, and topic time. Here's a quick overview of the schema. It's non-exhaustive. And hopefully, we'd like the schema to contain information that's useful for downstream HLT tasks. So for example, for information extraction, I already mentioned switch reference, which should help with co-reference. But there's also locative case, for example, that can help you extract places. There's things like evidentiality that can help you sort of determine the status of an event, whether it really happened or someone thinks it happened. And because we're trying to design the features in a sort of interoperable way, cross-linguistically, we're hoping that they'll be useful for MT. But we wanted to do some kind of evaluation of both of these assertions of utility. So the schema were designed so that labels would have roughly the same meaning cross-linguistically, but we wanted to know the extent of which that was actually true when we use them in real life. Furthermore, for languages that don't necessarily have a detailed morphological corpora available, maybe they just have a POS tagger, we wanted to see if we could transfer this morphological information onto them by projecting from related languages. And actually, this projection tagging technique came from David Yarowsky and colleagues a while back. So here's the experiments we did. And there'll be a picture of this in a moment that hopefully will make it more clear. So we found all the nouns and verbs in the New Testament of the New New International Version of the English Bible. And we used them as pivots. And again, there'll be a picture. Using standard MT tools, including the Berkeley aligner, we aligned this New Testament portion of this Bible to lots of different Bibles in lots of different languages. For those foreign Bibles, whenever we could, we assigned them UniMorph feature vectors, which we got from Wiktionary, and I'll talk about that, how we did that in a little bit. And we ended up with 1.6 million translations covering 47 languages across 18 language families. So here's what that looks like schematically. So if we take a pivot language, English, and we align everything to the English pivot wept that we can. So for example, in a Spanish Bible, we might align lloró to wept. In a Russian Bible, we might align zaplakal to wept. And again, there's two translations shown here, but we did this for lots of Bibles, so there would be more than two. And each of these translations has some kind of feature vector, which allows us to compare the corresponding feature values cross-linguistically. Basically, we do pairwise comparisons for translations that all align to the same English pivot to see how often they'll match or agree with each other. So here's some stats about how well that worked out. And these show average pairwise agreement under different genealogical language family similarity conditions. And you can see that it works reasonably well, especially if you're within the same family. It works less well for different families. The same language column represents different translations into the same language. So we would hope there will be good agreement there. Are you raising your hand? Yeah. Convenience. Because it was too difficult to align everything pairwise, so we wanted to align everything to a single language. Some of them were, but I'm not sure about the history of all of them. Yeah.
How did you define specifically? Just whether each feature.
Yeah. So for each pair of translations, we looked at their feature vectors, and we looked at the feature values in particular slots, and we just checked if they were the same.
So plural in English is translated into dual in some other language, that would be counted as a mismatch. Is that right?
Well, if one of the languages that aligns to English has a plural as its vector and another one has dual as its vector, then there'll be a mismatch. Yeah. Yeah, and there's some particular features that don't work well at all. As you might expect, gender is one of them because that's kind of a lexical feature that's arbitrarily defined in a lot of cases. And case is another one that works really poorly. And we think a lot of that is because languages tend to use case labels in extremely idiosyncratic ways. One example we found was in Russian, the instrumental case represents, I guess, temporal expressions, which is sort of specific to that language and doesn't really have too much sort of universal basis for it. So case is really problematic. And in addition to those kinds of sort of agreement statistics, we wanted to know how those things would hash out if you actually wanted to take an unlabeled language and transfer morphology onto it, and see how well that kind of naive tagging idea would work. So unfortunately, for a lot of these languages, we don't have morphological gold standard data. So we can only offer an approximation to how well projection tagging would work in this case. So one thing we did was take Albanian and Latin data that we just took from Wiktionary, and we just treated it as gold standard data. Then we did this same kind of alignment process, except we aligned everything to Albanian and Latin. We took a consensus, so the most common feature tag across all the alignments, and we checked if that corresponded with what we would see in the Albanian or the Latin. And you see it works okay. Again, certain features are more problematic than others. The holdout column is another approximation. It's basically if we take this situation where we align, yeah. No, we only looked at cases where both were defined. Yeah. Yeah. In the held out condition, we aligned everything to a single pivot, and then we held out one of the things that was aligned, and we compared its tag to the consensus of all the rest. And that got a similar accuracy number, with, again, case being particularly problematic. Okay, and again, this was a very naive procedure, so we'd like to think of it as a lower bound on the kind of performance we could get with better, particularly better modeling in the language we're trying to tag. Okay, so I've been talking a lot about using Wiktionary data in various ways. So all the UniMorph vectors that were talked about in that alignment phase before came from Wiktionary. And we spent a lot of time trying to get this data from Wiktionary because it's actually kind of a pain. So Wiktionary is one of the largest openly available sources of lexemes or lemmas with fleshed out morphological paradigms. Like Wikipedia, it keeps growing because people keep making new entries. Unfortunately, it's designed for human consumption rather than computer consumption, and there are basically no standards for how the tables need to look. So you can see here the same word, the same verb to say in both the Swahili and Kurdish Wiktionary. And you can see that while both tables contain a lot of similar information, so stuff about tense, aspect, person, and number, they're sort of aligned and oriented in very different ways. So the actual physical location of the cells is different in the tables. And what we'd like to do is sort of normalize across all that human variation and get down to a very simple database format where we just have inflected forms, their lemmas, and UniMorph feature vectors. So thankfully, while there is a lot of variation, a lot of the data we want is in HTML tables. So, and actually Roger Shui wrote the original code that made this work. We start with a generalized HTML table parser that works on service HTML directly. And the idea there is to associate inflected forms in the tables, like ouvre, to their grammatical descriptors. In this case, it'll be imperfect, indicative, and so on. And there's two major questions that come up here. One is, what happens when there's multiple potential descriptors for a form? So how do you know when to stop looking to the top of you, to the left of you, and to the upper left corner of you? So for example, how do we know that ouvre isn't infinitive and a gerund and a past present participle, and so on? And we just use a positional heuristic for that. Basically, we know that something can't be an infinitive and have indicative So we just note that indicative is closer to the word in question, and we resolve the conflict that way. An even worse question is, when we look at these tables, how do we even know what's an inflected form and what's a grammatical descriptor for that form? So how do we know that indicative is not a word in the paradigm, but rather a grammatical descriptor that applies to a word? So it turns out that Wiktionary variation is really bad. We tried all kinds of heuristics. We thought, oh, maybe they always bolded the grammatical descriptors. Maybe they're always in a particular color. None of that worked with any sort of consistency. So what did work for many languages was instead using a frequency-based cutoff. So the idea is that if you're an inflected form, you only appear in a couple of tables for a language. If you're a grammatical descriptor, you occur in a lot of tables for a language, because a lot of table types get reused. So we made some sort of threshold for deciding what's a form and what's a descriptor. And actually, when we did that, we were left with a relatively manageable size list of things that were potential descriptors that was small enough so that John and I can go through and assign each of them a UniMorph schema label. Okay, and we also extracted, there are other kinds of tables besides inflection tables, which are thankfully more standardized. We also got translations for words and derived terms for words when we could scrape them. So here you see the set of translations for the English word language and the set of derived terms for the English word flower.
Chris,
Yeah.
There's got to be, there's got to be a lot of words where the surface form is pretty ambiguous. I would think. Like, this is a nice, clean example, but...
Ambiguous in what sense?
Well, just appearing in multiple tables with different possible analyses. Or is that not the case?
So it, yeah, it shows up it can show up a few times, but it won't show up, thousands of times like a particular inflected form.
Okay, so the surface ambiguity is relatively limited, and that's true across languages.
Yeah, so I think you're unlikely to get a particular inflected form that's going to be a form for a lot of different lemmas.
But there is a lot of ambiguity, but maybe it's just within the page. That ambiguity is limited to. I mean, so if I give you surface form, the actual analysis is not clear at all.
Oh, yeah.
Most of that ambiguity, maybe then it's just limited within.
Right. So we don't treat the inflections in the cells as a set. So we just treat them as each cell is independent, and each one is associated with the corresponding stuff across from it. So we'll have multiple lines in our database for the same word with different tags or different feature vectors corresponding to whatever showed up next to them in the table.
What that's worried about is if you look at the table for English present tense, you get run. And so run showed up a lot of times, and then you dedupe within a page or something. But it may not make a difference because run is still going to show up much less often than the word singular. Singular shows up on every page.
Yeah.
So
Yeah.
okay.
Yeah.
In the same vein, but sure, related to the technique we talked about before, so with the same surface ambiguity problem, do you maintain multiple ones, for example, for Ablava, where there are two distinct correct feature techniques? Do you maintain both of them
So that's actually, you're talking about this? This is sort of a hack. What we actually did was remove anything that had multiple analyses in Wiktionary. So we only kept alignments that included stuff that only had one analysis. Yeah, and in fact, ambiguity. So we sort of completely punted on ambiguity resolution here. Okay. So this is just. Unfortunately, we obviously don't know a lot of the languages that show up in Wiktionary, so we're not really able to verify that the forms that people have entered are correct, from a linguistic standpoint. So we just choose to trust them. But our parser is still heuristic-based, so we'd like to get good performance out of that and be able to correct it whenever possible with minimal human effort. And we actually came up with a scheme for doing that uses this same kind of frequency intuition. So on average, each language uses about 123 unique HTML table types across all of its different pages. So there's that many table types for thousands of potential lemmas. So it's much easier for a human to go through and look at 123 different table types and say, oh, the parser is getting this right or the parser is getting this wrong, and sort of fix them and then apply that to every lemma. And the main thing that happens here is that a bunch of these table types are junk and can easily be filtered out of the database. For example, a lot of languages include the periodic table of elements, which, while possibly interesting, is not really an inflectional paradigm table. So that's what you see on the right there. And there's a little remove on it.
Think of nuclei as stems and electrons. Inflect something to get an ion.
Yeah, well. Yeah, so. Okay, so overall, with all of these tricks, we ended up getting around 15 million inflected forms out of Wiktionary for around 1 million lemmas across 350 languages. We also, as I said, we extracted all those translation tables and derivation tables whenever we could get them. You can actually get the inflection tables. I think they're all up there right now at unimorph.org if you'd like to use it for something. So it's data in this format down here, lemma language and UniMorph features. And we actually did this manual verification process that I described for a few languages. And we needed to do this because we needed to use this data for the next thing that I'm going to talk about, which is the SIGMorphon 2016 shared task. And so this was SIGMorphon's first shared task. It was the first shared task that I'm aware of on supervised learning of inflectional morphology. And it resulted in state-of-the-art systems on this task. It included 3 subtasks, 10 languages, 9 of which came from our Wiktionary database, and there were 9 systems submitted. And a lot of the co-organizers are here and came from JHU. So besides me, it was Ryan, John, Jason, and David Yarowsky, and also Mons Holden in Colorado. And thanks to Mons for some of the nice visualizations you'll see in the next couple of slides. Okay. So this is what the shared task looked like. It consisted of 3 subtasks, which were inflection, reinflection, and unlabeled reinflection. And each of these can kind of be reduced to the previous one. So here's the first task. In the inflection task, systems were given a lemma and a desired output UniMorph feature vector as input, and they had to produce an output form corresponding to that feature vector. So if you got run and you got a feature vector that said PS, third person singular past, you're supposed to produce ran. Similarly, if you got read and you again are told produce third person singular past, you're supposed to produce, well, red, right? Same thing, as best as you can. So subtask 2, slightly more complicated version, which we call reinflection. In this case, instead of a lemma as input, you are given an actual inflected form along with its UniMorph feature vector. So you were given the input inflection and the input analysis. You were given a desired output analysis, and you had to produce the corresponding form. So in this case, if you got sought and past tense as the input, and you were told, give me the infinitive, you were supposed to produce seek. And you can see how this can be reduced to the previous task. So if you can convert sought past tense into its lemma by doing some kind of lemmatization, and you get seek, you get back into this kind of situation from the first subtask. Similarly, the third subtask was just a harder version of subtask 2. In this case, you are only given the inflected form as input, not necessarily the lemma, and the UniMorph analysis was held out. And again, you had to produce, given just that form and the desired output vector, the corresponding form seek. So you can see how this again can be reduced to the previous situation. So if you can do an analysis on sought, you end up with subtask 2. And if you lemmatize, you end up with subtask 1. Okay. However, in this task, we didn't ask people to give us these intermediates. So we didn't ask them to give an analysis of sought. We didn't ask them to give lemmas. We always just asked for an output form. But presumably, the systems could have been implicitly need to solve these problems. So before I talk the results, which are actually interesting, I want to just briefly mention a little bit about the data. So again, we used paradigms from 10 languages, 9 of which came from Wiktionary. These were Arabic, Finnish, Georgian, German, Navajo, Russian, Spanish, Turkish, and Hungarian. The one that didn't come from Wiktionary was Maltese. That came from another source, the Gabra Open Lexicon. And because Wiktionary is so big, we were able to use all kinds of different morphology types. So German, Russian, and Spanish have a fairly standard morphology type that's been studied widely in the past and has been the basis for a lot of papers on this kind of thing in the past. They used they're suffixing languages along with occasional internal stem changes, which could be lexical or phonologically motivated. Their suffixes are fusional, meaning one single suffix can represent multiple abstract morphemes. So for example, in Spanish, the O ending is first person and singular and present. Turkish, Hungarian, and Finnish are agglutinating languages with vowel harmony, so they're also suffixing, but they have a more one-to-one ratio between abstract morphemes and suffixes. So not fusional like German, Russian, and Spanish. Navajo is a prefixing language with consonant harmony instead of vowel harmony. Georgian has circumfixing in its vowels. And Arabic and Maltese have traditional Semitic templatic morphology. So they do a lot of things using non-contiguous stem changes. And in fact, Maltese is the worst of the bunch because it combines the Arabic templatic morphology with a bunch of concatenative morphology borrowed through contact with Italian. When we gave people this data, we didn't give all the Wiktionary data. We wanted to simulate maybe a more realistic learning environment. So we gave them a sample of data where the probability that a form would appear in the training data was from a monolingual unigram distribution from a corpus, always Wikipedia dumps in this case. So here's statistics on how much data people got. There's one extremely obvious outlier. So in general, we tried to give people around 12,000 inflection pairs to learn from. For Navajo, we couldn't do that because there wasn't enough data in Wiktionary, so we gave them everything we had. And then for the surprise languages, Hungarian and Maltese, we gave them a little bit more data. This was really important for Maltese. because in our data source, Maltese had extremely massive paradigms. So thousands of unique forms per lemma. So we were oftentimes only able to provide one example per unique inflection type.
Sorry, by tags here, you mean
I mean full.
all the feature vector.
Yeah, so by tags here, I mean entire feature vectors. Yeah, I think I tend to use labels for individual features, but hopefully reasonably consistent. Okay. So of the systems that entered the shared task, there were, so Ryan separated them into 3 approaches. I'm going to simplify further and separate them into 2 approaches, those that use neural networks and those that didn't. And this is going to matter in the results. So the systems that use...
You can ask the audience to vote how for them.
Yeah. The systems that use neural networks, which included Munich, which was the best system overall, BIU MIT, and Helsinki, used typically recurrent neural network encoder-decoder architectures, which are also used for neural MT. The non-neural systems were often similar to previous approaches like DER and De Niro, and they tended to involve a string alignment phase, so between different inflected forms, learning transformation rules based on edit distance type stuff between the strings, and then learning when to apply those transformations in a CRF or semi-Markov model. So here are the results. The overall results, the green stuff is the neural networks. And it turns out that in a lot of cases, especially for the best system, the neural networks outperform anything else by around 10 percentage points across all tasks, across all languages. So that was pretty startling. We don't fully understand what the limitations of this sort of thing are yet. In particular, while we tried not to give people too much data to train from, 12,000 forms is still a decent amount. So it's interesting what might happen if we're in a really low resource scenario where we give people very few forms to learn from, especially since we know that neural networks tend to be data hungry to get optimal performance. So to see what comes out there, maybe stay tuned for future shared tasks in a similar vein as this one. Oh, sorry. These are average accuracies for the tasks for particular systems. The accuracy, so you never had to produce a tag in any of the cases. You always had to produce particular words. Yeah. So the accuracy is that you got the exact word correct.
Did everybody participate in every language?
I think so, yes. Some people, I think, weren't able to participate in Maltese for some of the tasks because I guess the size of the paradigms blew up their training systems or something.
Okay, so basically, for the most part, you had to do. So, I mean, some of these numbers aren't inflated, for example, just by doing only a subset of.
I don't think so. No.
Yeah. Okay.
I don't think so.
What's the first number outside the parentheses?
Oh, that's the average rank of the system across all the languages in that task. And the standard and restricted had to do with how much of the data you could use for training. Whether you could use data from other subtasks to augment the training set that we gave you for the task you were using.
And sometimes that's a significant difference in
Yeah.
like task 3 for the top system, and tasks 2 and 3 for the NSU system. Big problem in that system.
Yeah. So task 3 is the hardest because you actually you also had you had an embedded analysis step somewhere. And this is where you would have had to deal with this problem you mentioned, Matt, the ambiguity problem, where different forms get different. The same form can get different feature vectors. So there's probably some built-in error because of that ambiguity, although I'm not sure how much.
So how did you perform?
Oh, this is the oracle is an ensemble. It's basically asking, did any system get the right form? That is, if we knew exactly which system was right in each instance, this is the best we could do. Okay. All right. This is the linguistic aside that I mentioned at the beginning of the talk. So I thought it was pretty neat that the networks did so well at solving this morphological reinflection task. And a second question I wanted to ask was, well, if they do so well here, how well do they compare to human language learners? So I did a couple of experiments using the BIU MIT code base, which was the second best performing system in the shared task. And I compared that with some approaches from linguistics. So we know from the shared task that these networks should be great at learning lexical distributions. They get lexical data as input and did really well. I did a similar kind of experiment where I had the network predict the Romanian plural allomorph distribution for feminine and neuter nouns. And the network did better than the best current hand-tuned Maxent grammar for this particular task. But when linguists, particularly people doing morphology or phonology, talk about how humans generalized what they've learned about their language, they don't tend to do it with lexical statistics. They do a thing called WUG testing. So that's where they present participants in an experimental setting nonce word forms that don't necessarily exist in their language, but possibly could, and see how they react to them. So, for example, Albright and Hayes did a WUG test where they gave participants a fake English verb stem and asked them to produce its past tense. So for each stem, they had a particular regular instantiation of that past tense in mind and a particular irregular past tense form in mind. So for example, something like reift for rife would be regular, and rof for rife would be irregular. And then they counted how often the speakers in this experiment produced either the regular past tense form or the irregular past tense form. And there were about 25 speakers who were given each stem. And it turns out that the neural network does substantially better at predicting these production counts. So predicting the probability that people will produce a particular regular stem or a particular irregular output than the minimal generalization learner that Albright and Hayes themselves designed to solve this problem. So it seems like the networks generalize in reasonably human-like ways, at least with respect to going models in linguistics.
When both were trained on the same data set?
Yes.
So that data set was quite large, and it's possible that NVL would do better.
It's possible.
On 50 words instead of 12,000.
Yeah. So, well, the comparison is on a small data set. But yeah, you mean?
Okay, I'm sorry. Of course, this is on the previous slide under many, and you used the big data set.
Under, yes, this used a big lexical data set.
This next one here is the nonce word data set.
Yeah. The test is on nonce words, but the training is on lexicon.
How big a training?
Oh, I'd have to check, but I think it's a couple thousand plural singular pairs. Yeah. Yeah, but the WUG set is small, so there were 74 total. Okay, and here's another example of networks doing as well as linguistics models. So Becker 2011 had a hand-tuned sort of grammar for predicting when Turkish speakers would prefer to produce a laryngeal alternation on WUG stems. Laryngeal alternation in this case just refers to whether or not they're going to change the voicing on the last sound of a particular WUG stem when they add a particular affix to it. So whether ret would come out as redim or retim. And it turned out that the network matched the performance on their on their grammar, which is kind of interesting considering that in the paper they claim that it's impossible for sort of a domain general learning system without the appropriate linguistic bias, in this case not paying attention to vowels in the training set, could possibly learn the right generalization. But it seems to do pretty well, and the network doesn't actually know much about linguistic representations at all. All the training is done with raw characters being fed in on the input side. So no phonological features are known at training time. So it seems to work pretty well at approximating human performance, and I think it would be interesting to use it as a baseline when people develop these kinds of models in linguistics to account for this kind of WUG data. Okay, aside, yeah.
I actually thought about just that. What's the scientific questioning that linguists want to look at when they?
So it's typically in a kind of framework when they say, my theory is better than your theory because the model that instantiates my theory performs better on this data than the model that instantiates your theory. That better approximates how people respond to the WUGs. So in this particular case,
These are theories about what?
about how the linguistic learning needs to operate. So in this particular case, the theory in Becker 2011 is that people don't use a certain kind of vowel cue, so they don't learn from that, even if it's informative in the lexicon. And that ends up informing how they respond to WUG tests. So they don't use that vowel information when responding to WUG tests. That's the theory. And the way they show that in the paper is they show that a model that has that restriction, that basically ignores those vowels, does better than, in fact, this same minimal generalization learner that doesn't ignore those vowels, presumably. And the claim then is that a theory that doesn't include the right kind of linguistic bias in learning can't learn this generalization that well. And the idea here is that, well, it seems like a model without the right kind of linguistic bias can learn at least as well as the model they use. So that doesn't mean that if you added more bias to the neural network, it couldn't do even better. Okay, that's the aside. Back to morphology. So even before the share task happened, I was working with these recurrent neural network architectures to do, or attempt to do, morphological analysis. So, and it turned out that this particular kind of architecture is really simple to train and works decently well for the particular task of converting words into their component features. So for example, converting something like evimizden into plural, first person possessive, and ablative. And the architecture just consists of a LSTM encoder followed by a bank of independent softmax classifiers for each kind of interesting morphological feature. So you have a classifier for what the tense is, what the person is, what the number is, and so on. And I tried a number of variations of this architecture, like starting out with the one you see here, where you just encode the input string with a unidirectional LSTM and pass the last time step output to the bank of feature classifiers. And that works well as long as there's no interesting morphology at the beginning of the input string. It turns out that in order to get good performance for this in pretty much all cases, what worked best was doing a bidirectional LSTM and doing pooling on each of the time steps. What worked best was max pooling. It worked better than summing or averaging over the time steps. And I think the reason why that works better is pretty clear. It kind of absolves the network of certain kinds of memory demands. So in this kind of situation where you're only passing the last time step to the classifiers, the network needs to remember interesting stuff that happened at the beginning of the string all the way through the recurrent steps. But if you're allowed to use information from any of the time steps at decoding time, it's just much easier. So the network doesn't have to remember anything. If something interesting happens at the beginning, it can say something. It can say that it happened in its output and then forget about it.
Although this does left garden path, right? So if you're going left to right, and you say, oh, I saw this infix morpheme, and then some
Yeah.
then you just start with that.
Yeah.
And there's no way for that later step to cancel the
Yes.
guess that you made earlier, except maybe the network would learn not to pick the guess so early.
Yeah.
It's in the resulting step.
Yeah. Yeah. So that in that case, you would have to rely on the combination of the different. Basically, you would have to rely on a particular step saying, "Oh, I saw something interesting," and putting something in the output, and then a subsequent step saying, "Oh, that wasn't interesting at all,"
But under
and putting
max
like a
pooling,
negative.
you can't do that, right? Under max pooling,
Yes.
the earlier one would win.
Yes.
So I think basically, if anybody puts their hand up and says, "I saw this," they better be darn sure.
Yeah. Actually, I think there is a way for it to. Yeah, indeed, you're right. Yeah, doesn't work.
Although, well, if maybe there's a final layer or something.
I mean, there's max pooling followed by just a linear layer.
Yeah, okay. Well, that linear layer could actually fix it, because then I could put up my hand, but then you can put up your bigger hand later on.
Yeah.
And your hand has a bigger weight than my hand.
Yeah, and my other bigger hand could correspond to a negative thing in the linear matrix that's multiplying it that cancels out your earlier positive hand somewhere. Yeah. Okay. So yeah, which one am I looking at? Yeah. Okay. So trained a bunch of these. They're really fast to train, and as you might expect, it works really well if you look at the level of the individual feature vectors. So per feature accuracy, if you just want to know if something is plural or something like that, it works really well. But if you look at the combination of all the different feature detectors, it's not as good, especially bad in cases of syncretism. And part of that is because the different output classifiers don't constrain each other in any way. So the network doesn't know that if I see plural here, I really shouldn't be saying something else along some other feature classifier. So it doesn't work well at getting complete vectors correct. And it doesn't work well at doing lemmatization. So if you just attempt to replace each of these feature detectors with something that says, give me the letter at position 1 of the lemma, give me the letter at position 2 of the lemma, it's horrendously terrible. But after the shared task, we know that we can resolve some of these problems if we're willing to pay a cost of more training time, more decoding time, and a little bit more complicated architecture by using one of these sequence-to-sequence encoder-decoder architectures that got the state-of-the-art performance in the shared task. So the way these look usually is you have a bidirectional encoder, a unidirectional decoder, and some kind of attention mechanism in between. So instead of doing pooling of the time steps, the decoder can look selectively at each decoding time step at what was at each of the time steps of the encoder. And again, these architectures were designed for neural machine translation, so we can kind of hack their inputs to treat simultaneous lemmatization and feature analysis as a kind of translation problem and do them simultaneously. So the idea is, let's say we just convert the input word that we'd like to lemmatize and analyze into a sentence consisting of its letters. So swam becomes SWAM. And we convert the output word and its feature analysis into another sentence consisting of the words SWIM, double bar, or whatever separator, and then the features we want, like PST. So both of these are just treated as if they were sentences of words. And we can train the model to do these kinds of pairs, and it seems to work quite well. So I trained one of these on Farsi verbs using our Wiktionary database. Here's an example of the kind of output you get. You can get multiple outputs from the network by doing beam search of the decoder. And so for a particular input inflection, we get sentences consisting of lemma and features. It could, in principle, garble things, right? Because this is a really simple approach, right? There's nothing stopping it from putting, like, M's after the PST or whatever. But in practice, it often doesn't. And it's easy to filter out bad translations like that. And if we do some kind of analysis of performance, at least on Farsi, it works really well. The lemmatization is correct a lot of the time, even for the first choice of the network. And the complete tag sequence is correct a lot of the time as well. just the first choice of the feature vector. Okay, so I'll quickly switch and talk a little bit about where we can include morphology stuff in NLP timelines. In NLP pipelines. And I'm mainly going to focus on MT. That's because we've actually been involved a little bit with that and have some results. So the first kind of task I'll talk about is translating from a morphologically poor language like English to a morphologically rich one like Czech and Russian. And it turns out that in that kind of situation, it can be hard to decide, because English doesn't really tell you very well, what inflection you should put on the Czech or Russian side, or which inflected form you should choose. So obviously a language model can help with that a little bit. But another thing we could try is to learn how English uses syntax and word choice to represent the target semantic distinctions represented by morphology in the rich morphology language. So the idea is to project the target morphology onto English, or a language related to the target language. Train an English classifier to tag English words as if it was Russian or Czech. And then use the classifier output as features to constrain MT. So this is what that would look like. You would project from something like Russian onto English the fact that certain nouns have certain cases. You would learn a classifier to label the English words with those cases. And then when you do MT into another language like Czech, you would transfer those tags again. You would basically constrain your output on Czech to say, oh, this word is probably an instrumental inflection. We've only done a little bit of experimentation with this. Hopefully, working with Matt and Rebecca, we'll have a better system up and running at some point. But what we did was, as a test, we transferred case morphology from Russian onto English by aligning Russian and English Bibles together, and trained a Maxent classifier on the English side to tag those Russian case labels. So in the Maxent classifier, we just use the word we're tagging and it's part of speech. Because it's easy to dependency tag English, we use the head of the word and it's part of speech, the dependency label to the head, any prepositional modifiers it had, hopefully stuff like in or whatever, or with, will be useful for marking instrumental case, and determiners. This is actually kind of a similar idea to stuff that has been done before. One paper is Avramidis and Phillips' paper that actually did a similar kind of thing, but tended to use a lot of manual heuristics to figure out what the case should be on the English side. And it turns out that if we train on these projected Russian tags, and then with this classifier on held out projected tags, we get about 63% accuracy for case. So far, not that great. But again, as we saw at the very beginning of this talk, case is one of the types of features that translates over the least well. So maybe not that surprising. But a slight silver lining, if we train on Russian, and then we attempt to use those same labels and compare them to projected Czech labels, we get 60% accuracy. Basically what that means is we don't lose that much by training on Russian and testing on Czech, which is maybe good. Okay, and finally, I'll talk about, very quickly, the other direction. So before I talked about translating into a morphologically rich language, now I'll mention translating out of one. And the big problem there is sparsity. One way to deal with that is to lemmatize and segment into morphemes the input language. Another way is to deal with some of the sparsity blanks by basically creating synthetic bytext to feed to the MT training algorithm. And here's one way that could work. If we have some inflected forms in the source language that we got from monolingual data, right? We may have monolingual data, but not bytext. That includes these forms or a dictionary or whatever. We can run morphological analysis on them to get a lemma and features. And then there's two next parts of this process that different people are working on. as part of UniMorph. So hopefully you guys will hear more detailed CLSP talks about them down the line. But we have some means of converting feature vectors into English gloss templates, like I have VBN. And we have some means of translating foreign lemmas. So we can say bust or mock means to crush a rebellion in English. And then we can combine our gloss template and our new lemma to get a piece of bytext that consists of a complex inflected form and an English gloss for it. And we can add a bunch of these kinds of pairs to the MT training. And in some experiments that Huda and Philip recently did, that seemed to help. OK, so that's all the content I have. Check out unimorph.org and our SIGMorphon website for data and papers and things. And thanks to all my collaborators, and thanks to DARPA LORELEI for paying for it. OK. I think I may have used up an hour, so yeah. Yeah.
For the Czech-Russian piece, do you have any idea how the case pairs broke down by the input cases? Because I can imagine, like, nominative and tendency cases, you've got pretty easy, maybe Biography a little bit more complicated.
Unfortunately, I don't. I know that if we just labeled everything nominative, we would have gotten 34%. Correct.
But, like, I would imagine the structural cases together probably you have, like, 50%, maybe 40 to 50%. And then maybe if you throw in something, things like locative that are probably also just, like, more.
Yeah, I think we'll need to take a closer look at what happened. That was very fast. OK. Oh,
Actually, one question.
sure.
So you had any thoughts about taking the Wiktionary extraction and putting it back into Wiktionary to get people to produce stuff that's more machine readable? Like, for example, you could define just default template. I mean, there's some procedural things that Wiktionary could do that would make this easier down the line as you collect new ones.
Yeah.
It'd be a big effort, but it seems like.
Yeah, I think that would be super helpful. I think the other thing that, yeah, I think that would be super helpful if we could get Wiktionary to do any kind of standardization, but it might be rough to get people to agree to it.
So how does so when you create a new paradigm entry in Wiktionary, how does it work? Is there like a default table, or do you?
No,
just
no. So everything is done by cell. So let me go back to. All right. Oh, it's not showing. Sorry. OK. So everything is done by cell. So for each cell, we collect the cell contents as well as any labels associated with it. We put that in a row in the table.
No. So my question is, where does this table come from?
Oh,
does
it just.
Wiktionary, like, provide. So when I create a new, I want to create a whole new.
Oh,
or new
OK. So that depends by language. And I think, in fact, a lot of languages, these tables, and this is also kind of probably a source of errors that we haven't really looked into because we don't check the linguistic aspect of Wiktionary. A lot of these tables are actually generated with regular expression code. So the people enter, somebody has written up some kind of template that will create a set of regular expressions that will generate a bunch of these cells, given some subset of them. So people don't necessarily manually enter each cell.
So that an average person isn't going to be working with regular expressions, right?
Oh, they don't have to. Not in the surface HTML, but in the underlying code, there's some kind of template. So I think a person often just enters a particular number of cells, and somebody has written code to generate the rest of the table.
So there's some central organization that could possibly be improved.
Yeah, I think that code might also be written by users. So I'm not sure if Wiktionary itself is providing it. Yeah, I think if Wiktionary itself was providing it, likely you would get more standardization of the table formats. But it's actually really different, besides, inflection tables just being tables. Yeah. Persian required extensive hacking. Because in Persian, because I guess they were using Arabic ordering rules, they put the labels for the words on the right side instead of the left side, which completely borked the default parser. So, yeah.
Along those lines, I mean, there's associated on Wiktionary, they just have like a pronunciation of a particular word.
Yeah.
I mean, like if it was a standard for people to also include, well, they have the IPA, right? If they
Yeah.
also just include the tag from UniMorph.
Yeah.
If you got the trend going, right?
Yeah.
Maybe do a mechanical Turk kit where,
Oh, edit Wiktionary?
yeah, give people.
Yeah. That's an interesting idea. Yeah, but actually just provide them with what to enter, and then just have them do it.
Yeah, so there is precedent for this. There was a 2010 talk by Christo Kirov with Regina Barzilay, where they were automatically summarizing stuff in the medical literature and automatically creating Wikipedia articles.
Mm-hmm.
And then their evaluation metric was the number of edits they got was their loss function.
Yeah.
And there are some ethical questions about like creating life and then releasing it into the wild and seeing how many people it impacts. But still,
Yeah, that's interesting.
That reminds me of somebody
if you're accurate enough, there are other robots on Wikipedia.
Yeah.
so they're creating work for real humans, and that was the method. Is that, can I understand that right?
Well, I can't quite remember exactly how it worked, but they were.
Well, they didn't. They didn't.
Producing articles, and then the question was, did people think that things were wrong in the articles and had to edit them?
Yeah, so they weren't obligated to edit them, so they technically weren't.
Sure. But this reminds me
Yeah.
of Goldberg was complaining on Twitter. Somebody in some course, I don't know who it was, said you had to submit your student project as an email and paper.
Oh,
So, you're creating one.
thereby making more for reviewers.
Right, right.
Mhm.
With stuff that's not necessarily good.
Yeah. Okay.
Done? So,
Mm-hmm.
thank you.